Thank you, Olivier, for the introduction. So today I'm going to give you quite an overview of how we actually managed to make maps on Titan, because as you can see in the picture on the right, you have Rhea at the first in the foreground, when you can see clearly the crater on the surface, but on Titan we cannot see the surface at all. So let's start with the first actually resolved image that were acquired by Pioneer 11 in 1979, where we do have multiple pixels on Titan for the first time, but basically we can see almost nothing on this picture. So the actual decently resolved image was acquired by the Voyager 1 and Voyager 2 spacecraft in 1980 and 1981. The spacecraft actually observed Saturn, its system, and all its moon, and took, I would say, a decent amount of picture of Titan. And in both cases, we end up with images which look like this one, when we see a very hazy atmosphere with no identified feature on the surface, mainly because the payload for the imager on Voyager was focused on the visible range, where the surface is actually not visible. So it was very interesting for atmospheric purposes, but for surface study, these missions were not very successful on Titan. And just, I wanted also to take this opportunity to highlight one thing is, you may have seen the image on the left quite often as the historical images of Titan, which is very orangish. It's mainly because Voyager didn't have a red filter on board. So the images on the left was color composite made with the orange, green, and blue filter. And if now we can, with the Titan spectra, we can extrapolate what would have been a red filter on Voyager, and you can see that actually Titan was never orange. Titan is yellow, like almost every ISS images from Cassini show. So if you happen to say that Titan is orange, it's just because you are misleading by the Voyager filters. So as it was said yesterday by Christophe and Emmanuel, the first hint of being able to see the surface of Titan through the atmosphere was from the paper from Katrin Griffiths in 1991, when she took an atmospheric model and realized that for very specific wavelengths in the infrared, it is actually possible to see the surface because the transparency of the atmosphere is pretty high at these wavelengths. So on the right, it's pretty smarter. On the right, you have basically for different wavelengths an idea of how deep they can penetrate the atmosphere, and they realize from these images, from these data actually, it was unresolved data at the time, that for some given wavelengths, like for example 1.3, 1.6, and 2 micron, it was possible to actually get some signal for the surface and derive some surface albedo from it. So this is not an actual image of the surface, but that's the first idea of that we were actually able to see through the haze. The first images of the surface was actually acquired by Hubble in 1994. This was done, that's orbital observation. And in 3 of the filter, it was possible to see that Titan has actually a very strong dichotomy between the leading side and the trailing side. And especially the region on the trailing side was much brighter, which correspond to the area which is known nowadays as Xanadu. And that was the first attempt to actually image the surface. So very quickly after that, so before jumping, it was Jonathan Lunin who mentioned that actually Voyager may have seen the surface. So I found the paper you mentioned yesterday. And if you really stretch the images and you compare with HST, actually you can't see the dichotomy that was observed by Hubble. And so that was a retrospective analysis in 2004. looking back at the Voyager data. But if you only have the Voyager data, I would have said that it's pretty hard to actually make sure that it is a real signal from it. So back to the ground-based observation. So the first actually ground-based observation of Titan that were resolved and that show some structure on the surface was performed by Athena Koustenis with the CFHT using adaptive optics in the wings of the methane bands. And quickly after that, many other studies on Gemini, Keck, and the VLT were actually able to see the same pattern. So in 2024, basically we had a first idea of what the surface of Titan should look like before the arrival of Cassini and Huygens. So I would say that's the starting point of the Cassini mission as the initial guess to understand the surface. So Cassini arrived at the end of 2004, and right away with the VIMS and the ISS observation, it was very clear that the surface of Titan is actually observable by the spacecraft, especially in the wavelengths that was mentioned before in the paper of Captain Griffiths, like the 1.6, 2 micron, and 1.3. So on the left, you have different color images that were generated for different channels from VIMS. So on the top left, you have a very thick atmosphere, and after you can see the detail on the surface and even in the atmosphere. And on the right, I have put a UV observation of ISS during the first flyby of Cassini. So here you have the thick atmosphere that doesn't allow you to see the surface in the UV. But as soon as you turn the filters and you put a large band filter in the infrared, you can actually observe the feature very clearly and through the haze. And by the way, these two images were taken by less than 1 minute apart, and they are co-aligned. So you can clearly see how thick the atmosphere of Titan is. So that's something that many people forget is Titan is actually way larger, optically speaking, than its solid body. So we had a very nice talk yesterday on the Huygens landing by Eric Karkoschka. So I will not detail too much about this, but that's another representation of the movie he showed at the end of his talk. And we can clearly see that when you are high in the atmosphere, the haze is very thick. So you see pretty much nothing around you. And as soon as you get down to tens of kilometers above the surface, now you can start to actually resolve the features on the surface and up to the touchdown, actually. So having all these images taken during the descent was really important, but what is even more important is actually to put them in context. And it took a bit more than 10 years actually to get a consistent map and coherent about all the landing sites acquired by DIASA. So we went from just a landscape view down to an actual map that now can be compared with the other observation, as I will talk about it later on. So now I will focus more on VIMS, ISS, and the radar global map that were built throughout the mission. So that's an image that Christophe showed yesterday. So during the TA flyby, the first flyby of Titan by Cassini, we are already able to see the surface very clearly in some infrared windows. And even at that time, it was clear that Cassini was capable to do much higher resolution images than what all previous ground-based and HCT observation has done before. So very quickly after, we had more and more flyby, and we were able to complete the map step by step. So here you can see in just 1 year after, we had pretty much a coverage on the equatorial region. And after, in 2010, it's around the equinox for Titan, we had a very clear view of the equatorial region. We can recognize the bright feature on the right, which is the Xanadu area. And all the dark features are dune fields. And later on, it was possible to cover both poles during the summer equinox. And now we can have a view of the North Pole lakes, as you can see at the top. And in 2008, Stefan Lemulik published a global map of all the datasets from DIMS. So that's basically 19,000 individual cubes that were assembled to make this picture of the surface of Titan. So it still looks a bit patchy, I would say. You still have seams in the background, and there is a hole as well in the South Pole. But keep in mind that this is a view of, for example, the resolution of the individual cube. So it was a very long and dedicated work to actually being able to assemble all these things together to get something consistent in the end. So for ISS, the story is roughly the same. So right away after the first flyby, basically all the equatorial area was covered, and very rapidly it was possible to get very high detail around the equator with the improvement of the ability to process the images and to remove the contribution of the atmosphere. And so the mission evolved with an orbit which was a bit more inclined, so it was possible to see the South Pole in 2006. And the more we go towards the equinox, the easier it was to see the pole. So you see, you can start to see Kraken Mare at the top, and a bit of Ligeia in 2009. 2011, most of the North Pole was covered. And 2015, basically the whole surface of Titan was covered by ISS. And in 2018, Eric Karkoschka published this global map when he was able to actually remove all the seams from ISS with a very dedicated work in order to get consistent data sets all across Titan. And very recently, 2 weeks ago, a new ISS map was published. So there are still people working on these data sets to improve even more these results. For the radar, the radar is slightly different because with radar, you don't actually need to be in the illuminated side of Titan to see the surface because it's an active instrument. So you can map even on the night side, and I would say especially on the night side, and you get very high resolution in a short swath, but you can accumulate this swath all the time. So in 2011, that's the global coverage they had. And close to the end of the mission, that was almost the final map that was required. There is only a few flyby missing, but I didn't manage to find the actual last map with the latest radar swath. So as you can see, even at the end of the mission, the radar is pretty patchy. There is still many holes that was not covered by radar. And so even if it's in some places the highest resolution we had on Titan surface, it's not enough to interpret the whole context. So that's why, like Rosalie mentioned yesterday during her talk, in order to perform a geological global map of Titan, it was necessary to combine the different data sets from the different instruments to get a consistent view when we can clearly see the dunes at the equator and with the hammocky terrain, the plains in the mid-latitude, and the lakes mainly located at the North Pole. So now I want to emphasize a bit one of the work we did in order to combine these data sets, especially to combine the VIMS and ISS data sets, since they are both sensitive to the surface composition. So we start with the map from Stefan Lemulik. In this color scheme, we decompose this color map in different parts. Especially, we extract the luminance of the map, the green and red channel, and the blue and yellow channel. You get back the ISS map that you combine with the luminance map of VIMS that I showed before, and you recombine all the images, and you end up with that final map where we have a consistent view with all the ISS detail and the color from VIMS. That's, by the way, the globe that is behind me. So here it's a view of the North Pole. So VIMS is on the left, ISS in the middle. And when you combine the two data sets, you get the result on the right. So it's really useful in order to get even more detail from both data sets. Now I'm going back to the map from the ISR that landed roughly at the anti-Saturnian point close to the equator. And I have shown in this slide, at the top, you have the ISR map that I showed before. And you have the comparison with the three data sets, ISS on the left, VIMS in the middle, and radar on the right. And you can clearly recognize the feature that was observed by the ISR. So we now have a global view of Titan. In some places, we have regional scale with high resolution down to a couple kilometers per pixel, when we can clearly recognize the landing sites. And with the ISR, we have the map down to the surface. So the next step is going to be a Dragonfly that will land in the Cell crater, and ZB Turtle and Ralph Lawrence will talk about this in more detail later on. But here you can see our best knowledge of this area in the three instruments, and we expect to get a landing in this area in 2034. So now that Cassini ended, just to give you an idea of what we could get with GWST or with the Keck instruments nowadays on Titan. It's not much, but still we do see features on the surface, but it's not as resolved as what we had during the Cassini period. And I will leave Connor give you more detail on these observations later on. So here it's a summary of all these sequences that were necessary to build this map. So in red, you have the Pioneer and Voyager area. Almost half a Titan year later, in purple, you have the HSC and other ground-based observation. We had the Cassini mission basically during half a year for Titan, which was really important to actually observe both poles of Titan. So thanks to the extended mission. And now we are in the green part when we have, again, telescopic observation with GWST and hopefully with ELT in 2030. And the landing of Dragonfly will be in 2035, basically at the same season as Huygens landing on Titan before. So that's my conclusion. So Titan atmosphere is really unique in the solar system. Seeing through the haze is something very hard to do, but actually we were able to see it in some limited infrared windows, and it took more than 13 years actually to build global maps, but now we know its surface basically at kilometer scale level. And that's it for me.
Yeah, thank you very much, Benoit. So I have a quick question for someone interested in those global maps. Where to find them easily? I mean, is they are everywhere, or is there a single place to get those?
So they are a bit scattered on the internet for depending on which mission produce which map. They are not hosted at the same place, but one good place to find them is usually on the photojournal from JPL. That's the PEI images that I mentioned during the presentation. Some of them are in papers, actually. And the final one that I'm showing you here is available on the data.caltech repository. So you can, if you want it, you can download it from there.
And the updated geodetic map was just posted at the USGS as well.
Yes, Jonathan.
Well, since this is a celebration of history, I'll make a historical note. The radar coverage that you showed was obtained through blood, sweat, and tears because, as we have all, as has been already explained, the spacecraft instruments were bolted to the body, and so radar observations of Titan meant that the remote sensing instruments could not work. The INMS couldn't collect atmosphere. Of course, you couldn't do radio science during those passes either, and so there were many vigorous and sometimes acrimonious arguments among the teams. There were radar team members who were here, like Ralph and Rosalie and others, who really stuck their necks out to get these strips that we have there. It all turned out well in the end, but I have to say there were some very, very stressful disagreements that arose. Pardon? Oh, in the end it could. That's right, because you could. Yeah, okay, all right, I stand corrected on that. But for the optical remote sensing, yeah, you could not. So anyway, it was a strong effort by the radar team. Beautiful data. Can we buy copies of that globe somewhere? Is there consideration being made to replicate it so we could get copies?
Actually, that globe was made by, I think it's Astronomical Magazine. Since the map is public, basically pretty much anyone can do their own globe, so you can find it on the internet. It's way easier to get it from the US than it is from Europe these days, but at some point we may need to do a batch release of this globe for the Titan community. But yeah, just to comment one thing, with the radar, it's a trade-off with you get high resolution, so smaller footprints, so it's way harder to get global coverage. The ability for VIMS and ISS to actually acquire global coverage is because we were able to observe further out and to get larger view. And for the radar, that was not possible. It was only possible to acquire when we were very close.
It's always good to be reminded that when we see this product, they have been done via rigorous discussions. Okay, thank you, Benoit.